I mentioned yesterday how solving rational equations is quite easy. Solving rational inequalities isn't hard compared to a lot of the stuff we've done. This is not hard, but it's different. It's different in a very important way that if you weren't here today and you didn't learn this from somebody, you probably make a lot of mistakes. You'd probably guess at doing it the way we did stuff yesterday, which is wrong. You can't do it that way. So, you wouldn't get it. It's not the kind of thing you could necessarily teach to yourself, okay? But it's not hard, but it's different in an important way. You have to do it this way. And there's a couple of things that you kind of have to know about how to do it. But then it's not that bad. And it's similar to a lot of stuff that we've done with inequalities already. And so if you were good at solving polynomial inequalities, this is very similar. Okay. Before we get to the actual solving, we're going to do a little thinking activity here. When a function is positive, what does that mean about the function, about the graph of the function? It's above the x-axis. So that's like what we were just talking about when we were sketching. If you throw an x in f at x, some value of x, if you're going to get a positive output, what does that mean? It means the graph is above the x-axis. When a function, and we call that the positive part of the function. That's just what we call it, right? We've talked about intervals where it's positive and intervals where it's negative. We've talked about that in this course. When a function is negative, of course, that means it's below the x-axis. So you plug in some value for x, f at -2, or let's say f at 4, positive 4. If that gives you a negative result, the function is negative there at when x equals 4, and the graph would be below the x-axis. I know that's a simple idea, but that's going to be important for what we do today. So here's my question for you that I want you to think about, and you can write down some ideas before we take this up together. What properties of a function, we're talking rationals here, but any function that you can think of would be fine, would allow it to change from being negative to positive or positive to negative, vice versa? Either way, it doesn't matter. Okay? So under what circumstances would that happen? Where one moment a function is negative and the next moment a function is positive. I want you to think about that. You could write down some ideas. If you end up being wrong, you'll have to cross them out, but that's fine. You can brainstorm with the person beside you. Just have a minute or two to think about this. Consider a function. Some parts of it are positive, some parts of it are negative. What happens for it to change from positive to negative? So folks, one thing that you need to know here is we're talking about one function. I'm not saying like, if I give you a function, what could you do to it to change it so that it's no longer positive, it's negative? That's not what this means. Then it's okay if that's what you thought, because I just want you thinking about this on your own. It doesn't matter if you come up with right answers or whatever, right? It means for a particular function, so pick a function, bam. You got a function in your mind, whatever it is. It might be polynomial, it might be a rational function, could be a trigonometric function, whatever you want. Trig one might be good, a periodic function, because it's like always changing from positive to negative. It's positive, now I'm negative, now I'm positive, now I'm negative, now I'm positive, now I'm negative, now I'm positive, now I'm negative. What's happening during that change? Picture that one, because that's an easy one right there. And that's one of the properties. A particular trig function, sine of x. It's positive, now it's negative. What happened for it to change from positive to negative? What was the event? Thinking about the x's from left to right. Remember how with intervals of increase, we're always talking about x's. What happened? Literally, what did the graph do when it changed from positive to negative?
It changed direction and
went below the x-axis. So what does that mean? Between a point that's above the x-axis and a point that's below the x-axis, there's an x-intercept. So isn't an x-intercept a place where a graph would change from being positive to negative? On one side of the intercept it's positive, on the other side of the intercept it's negative, right? That's the property, that's one of them. That's what we're looking for. I'm going to give you 20 seconds, see if you can think of another one. Have you ever seen those like posts on the internet, or maybe your English teacher has talked to you about this, how like the human brain is an incredible piece of machinery, right? Biological machinery. Like, it's really, really amazing what it can do when you start to think about it at like a fundamental level. So when we read, we don't read letters. Our brains actually, as you become a good reader, your brain learns to read words as a whole. So like your brain actually more looks at the outline of the word, and that's how you become like a fast reader. And really fast readers, I think, can start to group multiple things together, and they kind of look at the shape of a whole group of words to read it quickly. Anyway, but isn't it interesting how your brain could like read, like even though half of those letters are, can you read that line? You don't even need to see the bottom half of the letters. You know what it says. Sorry, that was just an unimportant tangent. So does anybody know of another property? Like if you read ahead the next line, that probably should have been hidden for this exercise. What do you think? Asymptotes! Isn't an asymptote a place, a vertical asymptote, where like if I just picture a graph that looks like this, okay, let's get into this here. So if I have a graph like this, okay, and here's part of it, and then here's my asymptote, and here's the other part. So it's negative, it's negative, it's negative, it's negative. We get to an asymptote. On the other side of the asymptote, maybe not. Like this isn't a guarantee, but maybe not. On the other side of the asymptote, you're now above, right? So here's positive, here's negative. So vertical asymptotes. The other one we already talked about was X-Intercepts. So let's see, what kind of a graph should we draw? We'll do a polynomial graph. Oops. Okay, so where are the parts where this graph is positive? Where are the parts where it's negative? What is causing it to change from being positive to negative? X X-intercepts. There's one other that could happen. It's kind of related to, does anybody have any idea, any thoughts? It's kind of, this is a hard one. X-intercepts is kind of the easiest one to get. Vertical asymptotes maybe is something you could think about. The next one I think is really quite tricky. I guess it would be a hole. If you had a graph with a hole in it, which is kind of like an X-intercept, right? Because everything about the graph around there would be behaving as if that were an X-intercept anyway. And even in the algebra, you would have that factor on the bottom. You'd just also have it on top. So it'd be kind of like an X-intercept. But if you happen to have a hole, it's not technically an X-intercept. And you would have a place where a graph crosses from being positive to negative. Why do we have to talk about that? That will become apparent as we start to solve. Because with polynomial functions, how did we solve inequalities? We put them in factored form so that we knew where the X-intercepts were, because we didn't really talk about it, but that's where the graph changes from being positive to negative, or vice versa. And we could see where they were, and then we either used our understanding of functions, of the function itself, and the look of it, or you could do a little interval test, and you could see, is the function positive or negative here? And you would just do that little test, you draw that little number line, and then you write your final statement. Remember doing that? Solving polynomial inequalities. I hope you remember that. It wasn't that long ago. So we're doing very much the same thing. The difference is rational functions have more things that could happen. So it's not just X-intercepts. It's also vertical asymptotes that could cause a function to change from being negative to positive or vice versa, and then also holes. They don't happen as often, but it's possible. So what we need to do to solve a rational inequality is determine any asymptotes and X-intercepts, or holes, to find these transition points, or possible potential transition points. And we're going to test each interval, whether it's positive or negative, and then write our final statement. Okay? So none of this is too hard. If you have the skills that are needed so far for what we've done in this course, none of this is too hard, but it is quite specific, and there are little mistakes that people make. So, you know, it's kind of an important day for that reason. It's going to become apparent that if the inequality is not less than greater than 0, then we can't do anything. Because when I do my test, I'm going to test if something is positive or negative. Like, that's the only real test that we can do without finding exact values, which we do not want to do that. So as long as the right side is 0, when I test and I get a positive or a negative, I know if I'm above or below. Some of the other questions down the road are going to be like less than 1, which means that question is not ready to solve. We have to do some work with it to make it 0 on the right side before we can do our final solution. Okay, so that's going to be your first step. Always start by setting one side 0. And we'll find that sometimes takes quite a bit of work. But these two are both done for us. So what we're going to do is we're going to identify vertical asymptotes and X-intercepts. So I have an X-intercept of, should be able to just read it right off of there once you get a 0 on that side. Yep. 3, and a vertical asymptote of x equals -2. And often you'll have more, but in this case we only have those 2. When we did polynomial inequalities, we often actually sketched it. We're not going to do that here because you see how much more work it is to sketch. It's a lot more work. So we're not going to do that. We don't have to do that, but we're going to do a number line. And we're going to mark all of those points that we come up with, whether it's an intercept, a hole, or an asymptote. And I'm going to do a bit of a strange thing, where I'm going to mark my asymptotes looking like an asymptote. There's a reason why I'm going to do that, which will not be relevant for the first few examples, but it's going to come up later. So it's a nice little trick. I don't need the y-axis. I don't need the origin or anything like that in there unless it happens to be one of the intercepts. So this is my number line. And then here's what I'm going to do. I've talked about this before in this course, but we didn't need to use this technique, but now we do. I'm just going to go through every interval. So this is one interval. This is another interval. This is another interval. And I'm just going to test, is it positive or negative? Okay? And it's an easy test usually. Sometimes it gets a little bit messy, but often it's an easy test, especially when it's broken up into threes like this, because what value can I pick in this interval that's easy to work with? -3. That would actually be totally fine. What's another value in that interval? -4, -5. For whatever reason, I always like to pick -10. You could even go -100. As big and negative as you like it for this one, to make the math trivial in your head. Because watch what I'm going to do. -100 minus a little bit more is negative. So the top's going to be negative. -100 plus a tiny little bit is still negative. Okay? And -100 represents this interval. Because whatever's true for one value in this interval, it's true for all the values in this interval. Like, think about it. The graph is either positive or negative here, and it can't switch. If it's negative, it can't switch to positive unless there's a hole, an asymptote, or an X-intercept, and there isn't, because that's the first one, right? Like, there's a reason why we're doing this. So if I test any value in this interval, it represents the whole interval. So -100 works. I get a negative over a negative, which is a positive. So this interval is positive. And with polynomial functions, unless there was a reason to it, kind of flipped back and forth. With rational functions, it won't always. Not as often. Sometimes it will, sometimes it won't. So we really do have to test. What's a good value to test in this middle interval? 0 is a really good one to use when you can. You cannot use the value at the end of an interval. Like, I can't use -2 or 3. So if 0 is one of the intercepts or whatever, you can't use that, right? But as long as it's not one of those points, 0 is always one we're kind of going to use, because 0 minus 3 is negative, 0 plus 2 is positive. So this is negative over positive, so the middle interval would be negative. And then I'm going to pick 10. So 10 minus 3 is obviously positive. 10 plus 2 is obviously positive. 2 positives makes positive, so I've got it. And now I'm answering the question just like we did previously. When is it greater than 0? So when x is less than -2, and when x is greater than 3 is when the function is positive or greater than 0. That's our answer. Questions? We'll try the next one. Questions, questions, questions. Okay, so this one's very similar, except the numbers in this one are a little bit messier. Although, quite frankly, I think there's one down the road that's actually a little bit harder. This one's still not too bad. So I've got an X-intercept. Once again, you cannot afford to get your X-intercepts and asymptotes wrong. Like, if you get them wrong, basically the rest of the question falls apart. You might get part marks here or there for showing some understanding if I can tell what you're doing, but it really falls apart. So this is 5/2, and I have a vertical asymptote of x equals -4/3. So my vertical asymptote of -4/3 is here. And my x-intercept of +5/2 is there. This one is, when is it less than 0? So again, I'm going to pick a big negative number. 2 times negative 100 minus 5, that's obviously negative. 3 times negative 100, negative 300, plus a little bit more, doesn't matter, that's still negative. Do you see what I'm doing here? Negative over negative is positive. Pick 0, because then the x part just goes away. You get negative 5 over positive 4. That's going to be negative. The top is negative. The bottom is positive. When I plug in 0, pick a big positive number, like 10. 2 times 10 is 20. Subtract 5, that's not enough, right? I could see, what if this value, like I often use 10. What if one of my intercepts was bigger than 10, or one of my points was bigger than 10? Well, then don't use 10. Like, make sure you understand why we use those values. 10's an easy one to do. Use 100 is better. But if somehow we had an x-intercept past that, then 10 doesn't work anymore, right? That's not going to be a good test. So don't just get in the habit of using those numbers. Like, think about why. Okay, so I end up with a positive over a positive, which is positive. But this question was, when is this function less than 0? So it's only less than 0 in that middle interval. So we would write that, therefore, negative 4 over 3 less than x less than 5 over 2, right? So in this case, we have sort of those two possible answers. Good? Move on and try some trickier ones. What's different about this one? Yeah, we got to factor it first so that we can find where the x-intercepts are and the vertical asymptotes are. And we have to, this is like all the stuff that we've done in the past. Like, we have to put this into a format that we understand, that we know something about. Right? And that's always true of every kind of function we've done since even grade 9, but grade 10 in particular. Okay, so go ahead. And right away, we see that this one has a lot more intervals. This one is greater than or equal to 0. That's going to become really important in a moment. So my x-intercepts, go ahead and do as much of it as you can on your own. Don't wait for me. From left to right, we start at negative 4, which is an x-intercept. Then I have negative 3, which is an asymptote. Remember, I said it's important to show them differently on this little number line trick. Then I have negative 2, which is an x-intercept. Then I have 8. Scale doesn't really matter. It's just, I don't know, habit, right? I like to do it that way. Oh, and that is an asymptote as well. So far, so good? Everybody happy? When I pick a really big negative value, none of those are squared or anything like that. So, once you get used to this and sort of start seeing the way things work out, if you have all these linear factors, they're all going to be negative, right? Like, negative 100 plus 4 is negative, negative 100 plus 2 is negative, negative 100 minus 8 is negative, negative 100 plus 3 is negative. So all 4 of those are going to be negative. 4 negatives makes positive. I'm going to be positive there. I hope this isn't too hard, but it gets a little bit messier when I can't pick a nice interval. Like we used to use negative 100, 0, and 100. Now we can't because I've got negative 4 and negative 3, and I have to pick a value in that interval. So negative 3.5, I guess. I've seen people get this wrong because of the negatives and pick negative 2.5. That's not a value in that interval. It's not a proper test. Again, everything's going to fall apart if you do that kind of stuff. So it's really important, some of these easy steps, that you take the time and make sure you do it right. So negative 3.5. So I just look at each of them individually. Negative 3.5 is smaller than 4. So this one's going to be positive, right? I look at the size of the value that I'm testing with and the number there. And just ask it, which one's bigger? How does that impact it? So negative 3.5 plus 4, that's positive. 2 is smaller, so this is negative. 3 is smaller, so this is negative. And that one's subtracting, so it's negative. So I have 3 negatives. So it's negative here. I'll pick negative 2.5. I get positive, negative, negative, positive. This one's positive. I've added one more positive to it. Are you able to follow that okay? Negative 2.5 plus 4 is positive. Plus 2 is still negative because negative 2.5 is bigger. I'm subtracting, so that's obviously negative. But 3 is bigger, so that one's positive. So I got 2 positives there, so I'm positive. Now I can pick 0. So 0 means I've got 4 and 2 and negative 8 and 3, so I've got 1 negative overall, so that one's negative. And then if I pick a big positive number, they're all positive. If I pick 10, even 10 minus 8 is positive, so this one's going to be positive. So I got a lot of intervals here. And there's something really important that happens in this question, which is the reason why we include the asymptotes. And so as I am, and the fact that it says, when is this function greater than or equal to 0? Think about what that means, when it's equal to 0. Okay? So the first interval where it's greater than or equal to 0 is this first one over here. It's positive. So when x is less than or equal to negative 4, how do I know when to put the less than or equal to or just less than sign? Because of the question, but in this case it's going to include that point because at that point it's an x-intercept, so that point counts as well. I can see that some of you are already ahead of me here. You've already figured out what's going to happen next. That's awesome. What's my next interval where it's positive between negative 3 and 2? But how you write this is really important. So who has something to say about that? I saw a couple of hands. Jason, saw yours going up. Anybody else have something they've thought about this? Very nice. What do you think? Why is one of them less than, and the other one's less than or equal to?
Because with negative 3, like the whole point of it being asymptote is it can never touch 0, so it can't be.
Right, so it's not going to be equal. The function doesn't even exist at negative 3 because it's an asymptote. See why it's important to show it as an asymptote on our little number line so we know what it is? And just for when we're writing our final statement, we know if it's less than or equal to. And that only comes up when it's this type of question, right? If it's less than, it doesn't matter if it's an intercept or an asymptote because we're not including that point anyway, the threshold point. Does that make sense? To me, that right there, when you're doing a test on this, if you're getting all of these right, you get it. If you're doing all the work but getting that part of the answer wrong, you're kind of like you're doing the steps, but you're not really understanding why you're doing what you're doing, or you're missing part of the bigger picture. You know what I mean? That to me, that shows who's really, and that's fine if you're working hard and you're still not quite getting it. That's okay. That's life sometimes, right? But it's just that's what we're striving for. Be able to do the work, but also to be able to understand at a deeper level what we're doing and why we're doing it. And then the last one is going to be when x is greater than 8. Again, we don't include 8 because it's an asymptote, so it's never going to equal 8. So it's just when x is greater than 8. But that's also where this graph will always be positive. It would be awesome to go back. Actually, let's do it. I'm going to do it right now. We're going to graph this. Okay, so the top of this function, I'm going to graph the original function, was x squared plus 6x plus 8. And the bottom of this function was x squared minus 5x minus 24. So it's positive, and then at -4, it crosses X-intercept, and it's negative. And look, but there's an asymptote right here. So at 3, it does switch to being positive. Remember, it doesn't have to, because graphs can both do that, but this one turns out it doesn't. Okay, so it turns out that this one, it does flip from being negative down here to positive up here, and then again hits another intercept and becomes positive, and then again goes to this asymptote that's way over at X, and then becomes positive again, and it will always be positive after that because there's a horizontal asymptote, like, right? So it matches. All makes sense. Awesome. Okay. Whoa. Get that one started. This one's a quick one. Some of you might be asking yourself, get it started, what do you mean? How do I even get it started? Well, start factoring, put it in a form that we know something about. What do we notice? Yeah. So we have an x-intercept at -4 and a hole at +4. When x equals +4, make sure we know that it's when x equals, it's all about x's. And that's it. I mean, yep. Sure. Yep. I don't know that for this process you have to, but absolutely, like we would normally, yep. So I have an x-intercept at -4 and a hole at +4. I suppose it's also important to like show it as a whole on your number line, because if it was less than or equal to, greater than or equal to, if it happened to work out that it's not equal to that point because it's a hole, okay? To be honest with you, holes like occur in strange ways. Like this, it's rarely going to be relevant that there's a hole. If it ever really mattered that there was a hole, it would be a strange kind of particular question. But anyway. So when I put, Megan, to your point, if you wrote it as x + 4, your test becomes a lot easier. That's all you're kind of doing that anyway, but that's all you're plugging into, right? So if I put a big negative number in for that, -10 + 4 is negative, so this is going to be negative. And then I'm going to pick 0 + 4 is positive, and then 10 + 4 is still positive. So looks like we're good there. Yes?
When you have it as x + 4 is greater than or equal to 0, if you have it written like that,
yeah.
Can you just send the 4 to the other side and have that be your answer? The same final answer.
Yeah.
And then obviously include the whole of that.
But you have to, so how do we include the whole in our answer here? Do you know, Jason?
I was thinking we like match that x is not equal to 4.
Yeah, but so we're going to write it as two different intervals, but you're right. Like the function doesn't exist at 4. So it's not greater than 0 at 4 because it doesn't exist at 4. So the answer to this one is actually -4 less than or equal to x less than 4 and x greater than 4. Like we got to write the two parts to it because of that hole, because it doesn't exist at 0. Jason, yes, I think you would get away with that. If it was any other function where you happen to have more parts to it, you couldn't do that. Like you can have holes and still have a more interesting graph. So that's like, yes. But I wouldn't expect that to ever come up on a test. You know what I mean? So don't count on it, kind of thing. Any questions about this? Do you understand why we still had to, our answer still had to be written this way because of the hole? Okay. We only have 7 minutes here. We got more to do. We got some really important ones here to do because all the ones we've done so far, whew, this always happens. I run out of time. That's fine. We'll do one of these and we'll skip and move to the next one. I'm going to go through this fast. I'm going to do E fast. This is the first one that hasn't been already set greater than or less than or equal to 0. Right? And I'll remind you what we were doing yesterday. What would you do? You'd take that denominator, you'd multiply on the other side. In fact, I haven't even talked about this. Oh, here, we're really going to run out of time. Why can't you do that? Why are we doing all this nonsense with number lines? Why can't we just do it like we solved yesterday? Why are inequalities different from equations, equalities? When you first start doing inequalities, what's the most important thing that you sort of learn about solving an inequality? A little quirk with them. Something about the sign?
Let the denominators solve and you prove it, right?
I suppose that's kind of true. Not what I was thinking, but that's true. When you multiply or divide by a negative, you have to flip the sign, right? That's what I was thinking of. X plus 2, is it positive or negative? We don't know. You could do the whole case thing maybe, like we did with absolute values, but that's going to be a disaster if you have lots of parts. So this is the easiest way to do it. Okay, so that's the reason why we have to do this way. Have to. So folks, pay very close attention. This is what you do when you encounter this. And even though we're going to go over this example and you're going to practice it, unfortunately, probably some of you on the test when it comes up next week won't do it this way. You'll try to solve it like an equation and it'll just be wrong. Okay, because you have to solve these in a different way because of that sign flipping. What I have to do is I have to take the 1 and bring it to the other side. And I don't know anything about this graph. Because of that minus 1, all the graphs we've done have all the parts mushed together as one fraction. So I got to get a common denominator. And get everything together. And possibly after that, factor again, collect like terms, refactor, and figure out what's going on. This one turns out to be pretty easy. So I get x plus 3 minus, careful of the bracket, we talked about that yesterday, x plus 2 on top, subtracting the whole thing over x plus 2. So that's x minus x, which is just 0, and 3 minus 2, which is 1. So this ends up being 1 over x plus 2 is greater than 0, which ends up being a really easy one. So I'm going to kind of fly through it here because I want to get to at least one more example. So I've got a vertical asymptote when x equals negative 2. Asymptote. And before negative 2, negative 100 plus 2 is still very negative. So it's going to be negative on this side. And after negative 2, I could put in 0 here, or I could put in 10. 10 plus 2 is positive. So over here it's going to be positive. So when is it greater than 0? When x is greater than negative 2. Okay? There are several other examples we're not going to get to. I will do them and post them to the classroom if you want to see the rest of them done. We're going to do one more here. It's missing something. 8. Okay, so I've got to do collecting like terms and everything. I have to factor the bottom eventually anyway, so I'm going to do that now. So I'm going to do couple things at once. I hope this isn't too much at once for everybody. So the bottom is going to be, x plus 6 times x minus 3. So I'm going to bring the 1 over and subtract it, and I'm also going to, might as well turn it into what I need already. And this is a little bit weird. Do this how you like. But the top I want unfactored because I'm collecting like terms, and the bottom I want factored because that's how I need it in the end. So I'm going to write this version on top. And again, this is like, if you get this, if you get why I'm doing this, maybe not now, but eventually, then you're getting this stuff. You're really understanding why we're doing what we're doing and what the purpose of the algebra is, how it serves what we're doing. Okay, so I've got this minus this. You could do all of this in one step. I will write it out, even though we're running out of time here. Now I need to actually subtract. 2x squared minus 1x squared is x squared. Negative x minus 3x is negative 4x. And negative 1 minus 18 is plus 18, sorry, is positive 17 because it's negative 18. And I get x plus 6, x minus 3. Oh yeah, something really cool happens here. Very quickly. When I look at that, it does not look factorable. What should I do? So I'm going to check the discriminant and see what's happening on top. And in fact, when I do that, b squared minus 4ac is less than 0. Therefore, this has no x-intercepts. There are no real solutions to the top. So all I have to worry about in this case, and that could happen, where you would have to use, like that's a possibility for sure, where you would have to use the quadratic formula to find x-intercepts. Just because something's not factorable doesn't mean it doesn't have x-intercepts. It just doesn't have nice ones. I'm not saying it's going to come up in your homework or anything like that, but I'm saying it could. So in this case, I have two vertical asymptotes only of x equals negative 6 and x equals 3. And so when I do my number line, this is negative 6, and this is 3, and I pick my values, and so I'm going to pick something really big and negative, and I get positive and two negatives on the bottom, so this works out to positive. You'll just have to take my word for it. And the middle one works out to negative, and the top one works out to positive, so I end up with two intervals where it's greater than 0, and I'm going to write my solution. In this case, you would still be checking the top part for whether it's negative or positive. Although if you're smart, you could speed that up.